All right, we're going to take a look at finding the derivatives of the inverse trig functions. First, just a note about the notation. Some texts will use to indicate the inverse trig function. I know we've talked about this before, but some texts use this like superscript -1 to indicate that it's an inverse function, and other texts, including our text and my notes, use the arc notation. So this inverse sign here that's using that -1 superscript is the same as arc sign. Most of the time I'm going to use arc sign, but depending on the text or other resources you might look at, they're going to use that -1 superscript. And the thing to remember, the thing that's most important, is that superscript -1 is not an exponent. It's not a -1 power. It does not mean 1 over. It's really the inverse trig function. So, and we've talked about these before, but just to kind of reiterate, trig functions are these functions where you plug in an angle and it spits out some value that we might conceptualize as like coordinates on a unit circle, or maybe ratios of sides of a right triangle. And then the inverse trig functions go backwards. So, for example, if sine of pi over 6 is 1/2, that means that arc sine of 1/2 is pi over 6. It's the going backwards function. And we talked about this a bit, at least for the most part. I probably used arctan more than anything because we need to use that with vectors and when we're looking at inclination of a line. So we've got some formulas that tell us the derivatives of these inverse trig functions. And so we've got arc sine, arc cosine, and arctan. The arc sine and the arc cosine look pretty similar. In fact, the only difference in the derivative of arc sine versus arc cosine is that the arc cosine function has that negative in front. And arctan is the one that looks different. It's the one that doesn't have the radical involved. You don't have to memorize these formulas. These will be provided for you on any tests. There's like a sheet of trig formulas that you can have access to when you take your test. So we're going to start out with an example. And we're going to find the derivative of the inverse sine of 4x. So like I did with the trig functions, I'm just going to emphasize that this is the argument. I put parentheses around the argument. So y is the inverse sine. I'm going to rewrite it as arc sine. I kind of like that notation better. And now we'll take the derivative using this formula up here that we have. So dy dx is going to be 1 over, now in this case u is the argument inside of arc sine. So 1 over the square root of 1 minus the square of 4x. And then times du dx, so that's times 4. We'll simplify this. We have 4 over the square root of 1 minus 16x squared. Our next example, we've got a 20 Newton force acting on a sine. So the force is a vector. It has magnitude and direction. The direction is that angle theta that we see there in the diagram. There are two components, right? We have an x component and a y component, just like we saw with the velocity, which was a vector. Force is also a vector, so it has these components. Now what we know is that the magnitude of the force vector is 20 newtons. That's the length. And we're going to first express the angle theta as a function of f sub x. And then we'll get an expression for the instantaneous rate of change of theta with respect to f sub x. So I'm going to take this figure here. I'm going to just draw it a little bit bigger. We're not really concerned with the y component, so I'm just going to kind of pull out this right triangle that we have here. I'm going to draw it bigger. So there's our angle theta. The magnitude is 20 newtons, so that's the hypotenuse. And the f sub x is this side at the bottom. So if I wanted to make an equation that relates f sub x to theta and the hypotenuse, you think of SOHCAHTOA, we're going to use the cosine function because cosine is adjacent over hypotenuse. So that gives us f sub x over 20. Now we're not quite there yet where we want to be because it says express the angle theta as a function of f sub x. What we've done right now is just express cosine theta as that function. So if I want to pull the angle out, this is where I'm going to use the inverse function. So I'm going to use arc cosine. If cosine theta is equal to this fraction here, that means theta is arc cosine of f sub x over 20. So that's the first part. We've expressed theta as a function of f sub x. So now what we're going to do is find the derivative. So I'm going to take this function. I'm just going to rewrite it here, give myself some space to work it out. Arc cosine of, now instead of f sub x over 20, I'm going to just write that as 1 over 20 times f sub x. It'll make the chain rule part a little bit more clear. But if we take the derivative, we get d theta d f sub x equal to, let's see, the arc cosine formula is this one here. So a negative 1 over the radical 1 minus u squared. So negative 1 over the square root 1 minus f sub x over 20 squared times. Now the reason that I rewrote this argument as 1 over 20 times f sub x is because I find it helpful to see that as really just a coefficient, some number, times the variable. So now when I'm applying the chain rule, I know that just means I'm going to multiply by 1 over 20. I don't have to use like the quotient rule or anything. Now this expression we have is the derivative, is d theta d f sub x, but it's not really simplified. I'm going to do some work to simplify this. So 20 times the square root of 1 minus, got f sub x squared over 20 squared inside. And now I'm going to do one more thing to simplify. I'm going to take this factor of 20 and I'm going to pull it inside the radical, which I can do as long as I square it. So I've got 20 squared times 1 minus f sub x squared over 20 squared. And then I'll distribute and get see, 20 squared is 400 minus, when we distribute the 20 squared to this term, right, it'll cancel out that 20 squared, so just f sub x squared. And there's a nice simplified expression for the instantaneous rate of change of theta with respect to f sub x. If you didn't think about simplifying the radical, like some people will express that 1 over 20 as a decimal, 0.05, and they'll have some decimals in their expression. That's okay. I'm just a fan of having nice whole numbers whenever possible. Oh, let's try another. We're going to find the derivative of this function, arc sine x plus x times the radical. So the arc sine x part, that's actually going to be pretty simple because there's no chain rule to worry about. We're just going to use that formula. So the derivative of arc sine is 1 over the square root of 1 minus x squared. The chain rule would just have us multiplied by 1, so I'm going to leave that off. Plus, now, this here, this is a product. So let's set this up. And we've done product rules on this, right? This is the type of function that we would work with back in chapter 2. So our f function is x, which means f prime is 1. Our g function is 1 minus x squared to the 1/2 So g prime is, using the power rule, 1/2 times 1 minus x squared to the negative 1/2 times negative 2x, so we could simplify that as negative x times 1 minus x squared to the negative 1/2. Okay, so coming over here, g times f prime is 1 minus x squared to the 1/2 times 1 plus f times g prime, so that's x times negative x times 1 minus x squared to the negative 1/2. I'm going to clean it up just a tiny bit before we start the simplifying. So at this point we have a choice when we simplify, because if you scan this, right, we have this 1 minus x squared, right, showing up a bunch of times. So I want to be consistent, either switch to everything to write it in using exponents or everything with radicals. It'll make it easier. It doesn't matter which choice, like you still get the right answer regardless of the choice. I'm just going to go ahead and decide to put everything in a radical form. It looks like that. Now I can see this as adding and subtracting fractions. This middle term, I'm just going to put it over 1 to make it look like a fraction. I can get everything into a common denominator. The middle guy just needs a factor of radical 1 minus x squared on the top and the bottom. So there's our common denominator. And then we have 1 plus, our next term comes from multiplying these two. So I'm just multiplying a radical by itself. That's going to get rid of the radical. This is going to be 1 minus x squared, and then minus x squared. So we have, simplifying the top, 2 minus 2x squared over the square root of 1 minus x squared. I'm going to factor out a 2 up top. And we could still do some more, right? If you look at this, I've got the 1 minus x squared on the top and the bottom. There's a couple different ways you could think about it. One way that I think is kind of simple is to say, well, this 1 minus x squared, this factor up top, that's the same as having the square root of 1 minus x squared and then squaring it. And in that way, we can see that one of those square roots on top will cancel with the square root in the bottom, and we get 2 times the radical 1 minus x squared for our derivative. Okay, let's do one more. We want to find the slope of the line tangent to the curve of the function y equals arctan x over x squared plus 1, where x is equal to 3. So if we want the slope of a tangent line, that means we're going to find the derivative and evaluate the derivative dy dx and evaluate it when x is equal to 3. So we've got to cue up the quotient rule. So the f function always on top, this is arctan x. F prime, I'm going to just scroll back up here. F prime, this is the formula without a radical. So 1 over 1 plus u squared. One over 1 plus, in this case, x squared. And the chain rule would just have us multiply by 1, so I'm going to leave that off. G is x squared plus 1, which means g prime is 2x. dy dx is g f prime minus f g prime all over g squared. So that is g times f prime. So I've got x squared plus 1 times 1 over 1 plus x squared minus f times g prime. That's arctan x times 2x. This is all over g squared. We can do some simplifying now. In particular, in the numerator, we can cancel this x squared plus 1 with this x squared plus 1, or 1 plus x squared. We just get 1 minus, then we have 2x arctan of x all over the square of x squared plus 1. There's the derivative as a function of x. Now what we want to do is evaluate it when x is 3 to get that slope of the tangent line. Now because this function involves a trig function, or actually an inverse trig function, we're going to make sure that our calculator is in radian mode. Everything always in radians, unless it's stated explicitly that you need to use units of degrees or something. So we have 1 minus 2 times 3 arctan of 3 all over 3 squared plus 1 squared. So 1 minus 6 arctan 3 all over 10 squared is 100. So let's see what we get. I'm going to put the numerator in parentheses. I get negative 0.0649. So decreasing ever so slightly.